We're going to talk about forming molecular orbitals from atomic orbitals. We've seen this once before, where two hydrogen atoms come together to form a dihydrogen molecule. We'll start there, but we'll find there are many different combinations of orbitals that can interact in many different ways. We want to be able to draw the resulting molecular orbitals to show where the electrons are likely to reside. We'll begin with sigma-type interactions. As we saw with dihydrogen, we can start with two s orbitals on atoms far enough apart such that there's no interaction. Now we'll bring the two atoms together such that will allow overlap. Let's redraw the nuclei closer together and redraw the s orbitals. Looks kind of like a Venn diagram, but mathematically what we're doing is we're adding the two mathematical functions together that are responsible for the shapes. And we focus in on the overlap region in there. If there are two positive values, we should get a bigger positive value as we expect in constructive interference. So we can redraw this to try to show there's more electron density between the nuclei. We have added two atomic orbitals to form a molecular orbital. Notice that where they first touch will be at one place directly between the nuclei along what is called the internuclear axis. This is called a sigma interaction. When we draw the molecular orbitals, we show that most of the electron density is between the nuclei. Because of this, there is actually a force to pull the nuclei toward the center of the molecule. We call this a sigma bonding molecular orbital, and we give it the symbol sigma. Again, this is sigma because most of the electron density is along the internuclear axis, and it is bonding because most of the electron density is between the nuclei. Molecular orbital theory says that if we mix two atomic orbitals, we need to form two molecular orbitals. The theory tells us that for the second combination, rather than adding two functions, we need to subtract one from the other. To draw this, we start with one s orbital. Now, since subtraction is the same as negative, what we'll do is on our second orbital change the sign, and we indicate that in the drawing by shading in the second orbital. Now when we bring them together, we'll put the two nuclei closer to one another, and we can see that in the overlap region, now we have positive adding to negative, which will cancel. So let's redraw this. Technically, it only cancels in one spot, and that would be a node where the function equals 0. We'll indicate that with the dashed line. But we'll redraw it showing most of the electron density in between the nuclei gone, and most of it outside the nuclei. Again, where these two orbitals first touch is along the internuclear axis. So this is, again, a sigma interaction. However, when we redraw this, notice where most of the electron density is. Outside the nuclei instead of in between the nuclei. Instead of being attracted together, the nuclei are exposed to each other and will try to move farther apart. This is called an antibonding interaction, where there is a force to push the nuclei apart. We'll give this sigma antibonding molecular orbital the symbol sigma star, where the star represents an antibonding molecular orbital. It may be puzzling as to why we add the functions and then subtract them. Because the theory says so is not a very satisfying answer. But if we look at the sigma interactions of p orbitals, it becomes clear as to why we have to. We'll define an axis system where the z-axis is left-right, the x-axis is up and down, and the y-axis is forward and back. As before, we'll bring orbitals together, and we'll say they specifically come together along the z-axis. Now, our labeling is somewhat arbitrary, but usually the main axis of a molecule is defined as the z-axis. So let's use pz orbitals. We'll draw one on the left-hand atom, put the nucleus in the middle, and we'll shade one lobe. Now, when we draw the second one, there are two possibilities. For the second one, we can draw it such that the shading, when they overlap, will match, or we can draw it such that the shading, when they overlap, is opposite. Clearly, we have to consider both combinations. For the first, when we move these two together, and again, we'll draw the nuclei closer to one another, we're going to be adding two functions in the overlap region that are both the same sign, which will give a greater value in the overlap region. We'll redraw this, showing a much bigger lobe in the overlap region and much smaller lobes on the outside. This is again a sigma interaction, and since there's more electron density between the two nuclei, this will be a sigma bonding interaction. For the second combination, when we bring these together, again, we'll draw the nuclei closer. But now in the overlap region, notice positive and negative overlap and will cancel out with destructive interference. We'll redraw this using a dashed line for the node, and we'll indicate there's very little electron density remaining in between the nuclei, and most of the electron density is now outside the nuclei. The nuclei are exposed to one another, they wish to repel, so this will be a sigma antibonding molecular orbital.